Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today my name is Muhammad Lagi Besnen. My metric number is AA191285 and I'm from section 6. Okay, today I want to talk about the PID control system, and my part is introduction. Why implement PID controller? Okay, the proportional integral derivative PID controller. The PID controller is widely employed because it's very unstable and because it is quite effective. One attraction of the PID controller is that all engineers understand conceptually differentiation and integration, so they can implement the control system even without a deep understanding of control theory. Further, even though the compensator is simple, it is quite sophisticated. It capture the history of the system, which is through integration, and anticipate the future behavior of the system through differentiation. Okay. Here are the log diagram of the PID controller. Okay. We have a controller, we have plant. Okay. The output of a PID controller which is equal to the control input into the plant is calculated in the time domain from the feedback error as follow. Okay, the UT equal to KP ET plus KI and different ET DT plus KP DE over DT. Okay, first let's take a look at how PID controller work in closed loop system using the schematic shown above and the variable E. Okay, this represent the tracking error, the difference between the desired output R. Okay, and the actual output. The error signal is fed to the PID controller, and the controller compute both the derivative and the integral of this error signal with respect to time. The control signal U to the plant is equal to the proportional gain Kp. Okay, time the magnitude of the error plus the integral gain Ki time to the integral of the error plus the derivative gain Kd time the derivative of the error. Okay, this control signal, which is U, is fed to the plant, and the new output is obtained Y. Is obtained. The new output Y is the then fed feedback and compared to the reference to find the new error signal, which is U. The controller take this new error signal and compute an update of the control output. This process continue while the controller is in effect. The transfer function of a PID controller is found by taking the Laplace transform of equation. Okay, here is the equation where is Kp equal to proportional gain, Ki integral gain, and Kd derivative gain. Okay, we continue with my other members. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum. My name is Sharifah Azila Betruslan. My metric number is A190235. I'm from section 5, and for today I will present about our group project, our group assignment. Okay, for introduction, describe 3 applications of PID controller in the industry. The first one is furnace temperature control. The second one is neutralization pH control, and the last one is batch temperature control. So let's proceed to the task.
So Assalamualaikum and hi, my name is Nawal binti Muhammad Adi. So today I will be describing the 3 applications of PID controller in the industry and domestic use. So the first one is the PID controller is used in temperature control of furnace because the feature of PID controller result in a moderate stable PV signal and permit the derivative period to efficiently correct the fault without extreme changes to either the FCE or the CO. And next, the PID controller also used in MPPT charge controller because to find the MPPT by giving a fixed voltage and current point to the PID controller, and once the weather condition is changed, the tracker maintain the current and voltage will be stable. And the last one is the converter of power electronic. The converter is an application of power electronic, and the PID is mostly used in converter. And whenever a converter is combined through a system based on the change of the load, the converter output will be changed. For an example, an inverter is combined with load, the huge current is supplied once load are increased. Thus, the parameter of voltage and the current is not stable, but it will alter based on the requirement.
Assalamualaikum warahmatullahi wabarakatuh. And hi, my name is Muhammad Zamil Shauki bin Hisham, and my number matrix is AA191167. Right. So for the introduction, okay, my part is describe one example of a controller other than PID controller. So I choose PI controller. As the name suggests, it is a combination of proportional and an integral controller. The output, also called the actuating signal, is equal to the summation of proportional and integral of the error signal. Now, let us analyze proportional and integral controller mathematically. As we know, in a proportional and integral controller, output is directly proportional to the summation of proportional of error and integration of the error signal. Writing this mathematically, we have this equation, and by removing the sign of proportionality, we have this equation. So we have the difference between the equation right here, the symbol of proportional. So where the Ki and Kp proportional constant and integral constant respectively. Advantages and disadvantages are combination of the advantages and disadvantages of proportional and integral controller. Through the PI controller, we are adding one pole at origin and one zero somewhere away from the origin, which is in the left hand side of complex plane. As the pole is at the origin, its effect will be more, hence PI controller may reduce the stability, but its remain advantages is that it reduced steady state error drastically. Due for this reason, it is one of the most widely used controllers. So for the schematic diagram of the PI controller is shown in figure 6, and the step input for the value of K equal to 5.8, Ki equal to 0.2. Its time response is shown in figure 7. At K equal 5.8, as a P controller, it was on the verge of instability. So just by adding the small value of an integral part, it became unstable. Please note the integral part reduce the stability, which does not mean that that system will be always unstable. In the present case, we have added an integral part and the system became unstable. So right here on figure 6, we can see this is the closed loop control system with PI controller. And on figure 7, this is the response of the system with K equal to 5.8 and Ki equal to 0.2. And thank you.
Okay, we continue with the part 2 activity. Okay, first, me Nakib is doing for the transfer function 1. Okay, here's the first the question asked to the Simulink model, and then here are the Simulink model that I have made in MATLAB Simulink. Okay, and then I'm run the simulation. After that, I get this graph. Okay, here are the step response for the simulating. Okay, number 4, the question asks, determine the system stable or unstable or marginally stable. From this, I can see that my graph is marginally stable. Okay, number 5, observe, record and tabulate overshoot, settling time and steady state error. Okay, this okay. uh Here are some how to get like this. Okay. Okay, we put the command in the MATLAB like this, and this we change to 0. Okay, and then we run. After that, we will wait for some minutes. Okay, until the okay, so the step response have been out. Okay, if we want to find the peak response, steady state error and settling time, we must zoom in the graph until there is a margin between the graph. Okay, and then we right click, pick characteristic, take peak response. Again, settling time, and lastly steady state. Okay, after that we zoom out the graph. Okay, and we can see these are what we found, what we want find for the report, which is the overshoot, settling time and steady state. Overshoot, the overshoot is none, settling time 0, and final value 0. No, final value and INF. Settling time no. Okay, after that we number 6, we just change the KP value, and then we get the overshoot. After that, number 7, we change the KP and KD value. The KI is constant, and the steady state is we will get 1 from the graph, but the formula is 1 minus 1 divide with 1 times 100%. 1 is this one is actual desired value, and this one the actual value, which is actual value is fixed. The fixed number is 1 is fixed and 100%. Okay, after that, number 8, we just change the KD and KI value. After that, we will conclude here are the from the graph that the most stable graph. Okay, and the conclusion for this transfer function is the best PID controller that perform the transfer function system is PD controller. When the PD controller is used, the system reach its own steady state error, which 0% and 0% of overshoot when the value of KD 9, KP 5 and KI is 0 is used. Okay, I think that's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
So let's start with the task or the activity. So I do the second transfer function, which is the 9 over s squared plus 0.6s transfer function. And this is the Simulink model which I developed in the Simulink MATLAB. And this is the step response that I got after clicking the scope. And based on the question number 4, I believe our step response is the stable underdamped system. And for the question number 5, again the overshoot, settling time, and steady state error based on the step response. And the overshoot is 72.9, the settling time is 12.8, and the steady state error, I use the formula of the desired value minus by actual value divide by 1 and times with 100, and I got the steady state error 0. So the final value is the actual value. Next, for the question number 6, the question asks us to vary the coefficient of Kp and maintain the Kd Ki to 0. So I use the value 5, 10, and 15, and this is my overshoot and settling time and the steady state error. And for question number 7, the question asks to choose the best value of the 3 values of Kp, which is I choose 5 because based on the graph, the best value, the graph start to be stable when I use the Kp equal to 5, and the overshoot is 86.9, settling time is 12.7, and the steady state error is equal to 0%. So I use the Kp equal to 5, and the value of Kd I vary with the value of 3, 6, and 9. And based on this tabulation, I can see that the graph start to have its own steady state error and overshoot when I use the Kd equal to 9, which is the overshoot is 0, the settling time is 0.0486, and the steady state error is 0%. So for this question, I choose the best value for Kd is 9, and I vary the value of Ki is, I use the variation of value of Ki is 10, 20, and 30. So the best overshoot that I have for this question is 0.0576, and the settling time is 0.0482, and the steady state error is also 0%. So in conclusion, for the second transfer function, the best PID controller that perform the transfer function system is PD controller, because when the PD controller is used, the system reach its own steady state error, which is 0%, and 0% of overshoot when the value of Kd is equal to 9, the value of Kp is equal to 5, and the value of Ki is equal to 0 is used. So I think that's it from me. Thank you.
Hi, Assalamualaikum. My name is Sharifah Azila binti Ruslan. My metric number is AA190235. I'm from section 5, and I represent about our group project or group assignment, which is in this group project, I will take over for the transfer function number 3. Okay, in the activity, the first question is we have to develop the Simulink model in MATLAB. Okay, so this is my Simulink model for the transfer function number 3. And after that, we have to run the simulation to get the step response. Okay, so here is my step response, and my step response show that my system is stable, which is under damped. And after we got a step response, we got a step response, we have to observe, record, and tabulate the overshoot, settling time, and steady state error. Okay, so we have to do a coding in the MATLAB, and this is my coding to find the overshoot and settling time, and also steady state error for the transfer function number 3. Okay, so after write the coding in the MATLAB, we have to run it. Okay, so here my step response, and we have to find the overshoot, settling time, steady state error. Okay, so my steady state error is 0.00498%, and my settling time is 3.02 seconds, and my overshoot is 78%. Okay, so after that, we proceed to the question number 6, which is we have to insert the three three different KP value to observe and record the overshoot, settling time, and steady state error. Okay, so as you can see in my report, I choose the number 3, 6, and 9, which is this three different value of KP value. We will get the different value also for the overshoot, setting time, and steady state error. And I will show you how to find the how to find the overshoot, setting time, and steady state error by using the value of KP. Okay, so let's say my first number is 3. Okay, so I run it. Okay, so number 3. Okay, so here we have to find the overshoot, settling time, and steady state error. So here my steady state error is 0.0148%, and my settling time is 3.01 second, and my overshoot is 78.1%. Okay, so same goes if I put the number, I insert number 6. We will get the different value. Okay, so overshoot, settling time, steady state error. Okay, so here is a steady state error, settling time, and overshoot. Okay, so we will proceed to number 7, which is we have to insert the different value for KD. Okay, so to find the value of KD, first we have to choose which value is show that our step response is more stable. So I decide to choose a number of 9. Okay, so I insert the number of 9 as my constant value to find the KD. Okay, which is the KD, we have to use a different value, and I choose the 1, 2, and 3. Okay, so KP is number 9, and KD, if I put number 1. Okay, so here overshoot, settling time, and steady state error. Okay, so steady state error, settling time, and overshoot. Okay, so after that we have to find the KI. Okay, so to find the KI, I choose the value of KD as a constant. To find the KI is 3, and the KP is 9. Okay, so my value of KI is very big, which is 400, 800, and 900. Okay, why did I choose the 400 and 800 and 900? Because I want to fulfill the system user requirement. Okay, so here you can see that transfer function from 1 to 3 is the requirement is overshoot is below than 10%, settling time is below than 2 seconds, and steady state error is below than 2%. So I choose the number of 400, 800, and 900. So you can see that the overshoot is 0%, settling time is 1.98 seconds, and steady state error is 1%. Okay, so here, okay, if I put 400 instead of 400, okay, so the overshoot, settling time, steady state, okay, so 1, 3. 1, 9, 3. 9, 3, and 400. Okay, so my peak response. My peak response is 0%. Settling time is 1.98 seconds. Steady state error is 1%. So the conclusion is for the third transfer function, the best PID controller that perform the transfer function is PID controller, because when the PID controller is used, the system reach its own steady state error, which is 1%, and the overshoot is 0% when the KP is 9 KD is 3, and KI is 400, right? So that's all from me. Thank you.
Right. So now I'm going to explain about the transfer function number 4. Right. So right here we have Simulink model 4 is the transfer function. Okay, and this is the Simulink model. Okay, the block right here. Okay. So the question needs us to observe and record the step response. So I have done it, and this is my result. Okay. Okay. And number 4, okay, determine whether the system is stable, undamped, overdamped, critical damped, unstable, or marginally stable. So this system is unstable because of this waveform. Okay, for number 5, observe, record, and tabulate the overshoot, settling times, and steady state error. So this is my result. I got this step response. Okay, by there I can find the overshoot, settling settling time, and also the steady state error. Okay, that is for number 5. For number 6, 7, and 8, okay, I have used this command on MATLAB, okay, and I replace the value. For example, number 6, it say that we must try 3 different KP value. So right here, the first one is KP equal to 0.1. Second one is KP equal to 0.2, and the third one is KP equal to 0.3. Okay, I have I have modified the value of KP. So by using this command, I replace the value of KP, and I get this result for number 6. For number 7, okay, we need to modify the value of KD, okay, which is the first one is 0, KD equal to 0.1, KD equal to 0.2, and the third one KD equal to 0.3. Meanwhile, the KP value is changed by 0.1. Okay, KP equal to 0.1. Same also by KI equal to 0. Same. And I got this result for number 7. The steady state error for these 3 same. And for number 8, we replace the value of KI by replacing KI equal to 0, KI equal to 0.0001 for the second, and the third one is KI equal to 0.0002, and this is my result for number 8. And the last one, okay, number 9, I get this result by by replacing the value of KP equal to 0.1, KD equal to 0.1, and KI equal to 0. And this is my result for number 9. So for the fourth transfer function, the best P, I, and D controller that perform the transfer function system is PD controller. When the PD controller is used, the system reaches its own steady state error, which 1% of and 0% of overshoot when the value of KD equals to 0.1, KP equals to 0.1, and KI equals to 0 is used. So that's all from me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzat Daniel bin Muhammad Isa. My number matric is AA191531. So today I will present my part in this group project, which is part 3, the overall conclusion. As you can see here, there are two things that we need to conclude. Okay, the first one is we need to conclude the effects of P, I, and D coefficient for each transfer function. After we do the group project, we find out that it can be easily concluded that the proportional term is maximum responsible for change in output. The integral term is responsible for decreasing the steady state error, and the derivative term is responsible for decreasing the rise time, and overall PID control is responsible for better results due to the decrease in settling time. So the second one is we need to conclude which controller performs best for each transfer function. Okay, first thing first, we need to understand how the implementation of PID controller in control system works. Okay, we know that P control's output power is directly proportional to control error. The higher the proportion coefficient, the less the output power at the same control error. Proportional control can be recommended for fast response system with a large transmission coefficient. Okay, next, PI controller. PI controller is mainly used to eliminate the steady state error resulting from P controller. However, in terms of the speed of the response and overall stability of the system, it has a negative impact. This controller is mostly used in areas where speed of the system is not an issue. Since PI controller has no ability to predict the future errors of the system, it cannot decrease the rise time and eliminate the oscillations. If applied, any amount of I guarantees set point overshoot. Moreover, we also know the aim of using PD controller is to increase the stability of the system by improving control, since it has an ability to predict the future error of the system response. In order to avoid effect of the sudden change in the value of the error signal, the derivative is taken from the output response of the system variable instead of the error signal. Therefore, D mode is designed to be proportional to the change of the output variable to prevent the sudden change occurring in the control output resulting from sudden change in the error signal. In addition, D directly amplifies process noise. Therefore, D only control is not used. Last but not least, PID controller has the optimum control dynamics, including zero steady state error, fast response, which is the short rise time, no oscillations, and higher stability. The necessity of using a derivative gain component in addition to the PI controller is to eliminate the overshoot and the oscillation occurring in the output response of the system. One of the main advantages of the PID controller is that it can be used with higher order process, including more than single energy storage. In conclusion, the aim in using the PID controller is to make the actual motor speed match the desired motor speed, and PID algorithm will calculate necessary power change to get the actual speed. This will creates a cycle where the motor speed is constantly being checked against the desired speed. The power level is always set based on what is needed to achieve the correct result. By using PID controller, we can make the steady state error zero with integral control. We can also obtain fast response time by changing the PID parameters. PID controller is also very feasible when it is compared with other controllers. Therefore, it is clear that PID controller performs best for each transfer function. I think that is all from me. Thank you for listening.